Hello class, welcome to this AP Statistics lesson, lesson 3.2, least squares regression. So this lesson is very packed. It has a lot of content in it. We're going to talk about predictions. We're going to talk about calculating the least squares regression line, features of regression line. So this one's going to have a lot going on, and it's the core of the unit. All right, so here we go. So we have, let's talk about what a regression line is. So a regression line is a way to summarize the relationship between two quantitative variables. So last time we talked about scatter plots. So now we're going to take these scatter plots and we're going to impose a regression line onto these. So a regression line is, it's a line in y equals mx plus b, but just like the traditional slope-intercept form. However, in statistics, we use the regression line y hat equals a plus bx. So a plus bx. Rather than using mx plus b, we use bx plus a, or a plus bx. But you could see from this example that we have a regression line with the given equation y hat equals 38,257 minus 0.1629x. So we can identify our slope and our y-intercept from that. So a regression line is a line that describes how y changes as x changes. So the explanatory variable, recall, is x, the response variable is y. And like I said earlier, this is the equation. Now this is pronounced y hat, all right? And it's to be distinguished from y. So the y is, each of these coordinates right here are the actual data, and they represent the coordinate xy. Whereas a point on this line, this regression line, is x, y hat. Okay, so that's the difference between the y hat and the y, is that the y refers to the actual data points, right? The y hat refers to the point or points on the actual line, right? The equation. So that's the difference. So the y hat is, in other words, the predicted value of y for a given value of x. All right, so let's do an example where we have to make a prediction if we're given a regression line. So here we have a random sample of 16 used Ford F-150 Super Crew 4x4s selected from among those listed for sale at autotrader.com. The data are shown in the table. For these data, the regression equation is given by, so we have the y hat, so that's the price. So the price hat, if you will, this is like the predicted price. So the predicted price is equal to 38,257 minus 0.1629 times x, where x is the miles driven. Predict the price of a Ford F-150 that's been driven 100,000 miles. So here x is 100,000. So here the explanatory variable is the miles driven. In general, the more miles that are put in a vehicle, the more depreciation occurs, right? So the price tends to decrease. So in this case, the explanatory variable is x, right? Or is 100,000, is the number of miles rather. So x is the explanatory axis, and it represents the miles driven. Okay, so we have some data here as well for miles driven versus the price. Not only do we have the scatter plot, but we have the data and the regression line. And so from the regression line, you can see that if we want to predict the price for using the regression line, then for 100,000 miles, that's going to be right here, halfway between 80 and 120,000. We can see from the graph that it's around roughly 22,000, right? $21,000 to $22,000. That seems to be the predicted price. And notice that's not actually from the data, that's actually from the regression line helping us make that prediction. But we can also use the equation they gave us in order to make that prediction. So we can plug in 100,000 for x here and get our predicted price. All right, so we go ahead and put in 100,000 miles there. And then we get $21,967, which is roughly $22,000 from our prediction. All right, so now let's consider the question, can we predict the price of a Ford F-150 with 300,000 miles driven? Going back to the data, we can see that we don't have actual data for 160,000 miles, or for anything beyond 150 or so thousand miles, right? But we want to see what happens if we take it to 300,000. And that's what we're going to try to do. Can we predict that price? So we take the regression equation and we're going to plug in 300,000 into it. So by doing so, we get the calculation to be negative $10,613. So clearly this can't be the case, because we can't have the situation where we owe somebody money if we drive 300,000 miles. That clearly can't be the case, right? I mean, the price being negative 10,000. So there's clearly an error that occurred. And the error has to do with the model that the data that we collected. So what we did here was we did an extrapolation. An extrapolation is when you take a regression line and you make a prediction far outside the interval of x values that you used. So here the largest x value that we had was 150,000-ish miles, and so we're taking a prediction well outside, or just outside of that interval of the data that we collected, and that's called an extrapolation. They're often not accurate and they're nonsensical when you take them out, when you extrapolate too far. Okay, so what we did earlier in part A is known as an interpolation. So an interpolation is the opposite of the extrapolation. So an interpolation is a prediction within the interval of x values. So prediction within interval of x values. So when we made a prediction for 100,000 miles, that was an interpolation, and that was relatively accurate based off of the model that we had. But an extrapolation tends to be inaccurate, and it's something that is discouraged. All right, so don't make predictions using values of x that are much larger or smaller than those that actually appear in your data set. All right, so generally when we collect data, there's not going to be a perfect prediction, right? There's bound to be errors in our prediction, because what we're doing is we're taking the realistic data and we're trying to fit it to an ideal line, right? And so there's bound to be errors in the real world. So prediction errors are bound to happen, and so what we want to do is we want to minimize these errors, right? But these errors are called residuals. So in statistics, we refer to the errors in the vertical distance as residuals. Okay, so in this case, if this data point here has a y value of, for example, 35,000. So that's the y value for that point, and then the point, and this here on the actual graph, let's suppose it's around 27,000, right? It's around here. Then if that's about 27,000, let's say that that's my y hat is approximately 27,000. Well, then my residual is 35,000 minus 27,000, right? In that case, 35,000 minus 27,000, and that's equal to 8,000, okay? And so my residual is $8,000. So that means I over-predicted, or I under-predicted, right? So this is an under-prediction because my graph is my prediction, right? And my data point was above that prediction. And so that means that we under-predicted. So a positive residual means under prediction. A negative residual means we over predicted. All right, so that's how the residuals work. So a residual is the difference between the actual value of y and the value of y predicted by the regression line. So we have y minus y hat, okay? And if you want to remember it easily, remember it as AP, right? We're taking AP statistics, actual minus predicted. So that's an easy way to remember. Actual is y, prediction is y hat. And again, if the residual is positive, that means if it's greater than 0, then that means it's an over prediction, right? Or under prediction, I'm sorry, I keep saying over prediction. It's under prediction. If it's less than 0, then it's an over prediction. And if it's equal to 0, it's a perfect prediction, right? Which usually that's rare, and it's not bound to happen. All right, so here we go. So let's look at another example. Using the same data set, let's calculate and interpret the residual for the truck that was driven 70,583 miles. So this is the actual data point. So this is my y. And then my y hat, we have to figure out what the y hat is for that truck, for the number of miles driven. which is 70,583. Okay, so, or I'm sorry, this is my x value. I said that's my y value. This is my x value. Sorry about that. So that's my x value, the number of miles. And so what we're going to do is we're going to plug that in here to get the mile, into the miles driven to get the price, the predicted price. Okay. So first off, we want to find the predicted price. So the predicted price, we're going to plug in into that model, right? The regression line, the 70,583 miles. Okay, and the predicted price is 26,759. Next, we want to find the actual price, right? And so the actual price, if you look at the data set, is right here. So you can see that for 70,583 miles, the actual price was $21,994. And so we're going to subtract the price. You're going to do the price minus the predicted price. And we get a negative residual. Remember, a negative residual means we over predicted. So we predicted that it was almost 27,000, but it was actually almost 22,000. So we over predicted. All right, so that's how you calculate the residual. Now we're going to interpret that. So interpreting that means we're talking about the actual price of the truck is that much less than. So the $4,765 that we calculated, it's less than the cost predicted, right? Means that we over predicted, and so the actual price was less than predicted. Okay, so hopefully that made sense. All right, so now we're going to talk about interpreting the regression line. We know that the regression equation is y hat equals a plus bx. And remember that a is the y-intercept and b is the slope. So we're going to talk about the y-intercept first. So a, the y-intercept. Remember in algebra, the y-intercept is when x is equal to 0. So it's where traditionally you would cross the y-axis, right? And so that's when x equals 0. And so the slope is rise over run. And so remember that the slope means that as y changes, x also changes, right? So that's the rise over run. Now there's something to keep in mind about the slope. So remember, slope is rise over run, or change in y over change in x. So when we're talking about an example of a slope of 0.5, so let's say b is 0.5, then you can put that over an invisible 1, right? You could take any number and put it over 1, and it becomes a fraction. Okay, so I know it's weird because we have a decimal over a number, which means we have a decimal within a fraction, but that is definitely possible. So here we just have an increase in the y value of 1/2 unit for every increase in the x value of 1 unit. So that's what that's saying, is that when the y value increases by 1/2, the x value increases by 1. Okay, so you can read it backwards as well. If the x value increases by 1, the y value increases by 1/2. Now if we have a negative 0.5 slope, then we can put it over an invisible 1, right? We'll just write it out. And so it's a decrease in the y value of 1/2 for every increase in the x value of 1 unit. And so that's how you generally interpret the slope. And it's going to be very useful when we interpret it in context. All right, so let's go back to the Ford F-150 example. So we want to interpret the slope here, and then we want to see, does the value of the y-intercept have meaning in this context? So let's take a look at the slope. Well, we know that the slope is negative 0.1629. So that means that we could put that over invisible 1, and that means that when we're looking at the predicted price, and you want to include the word predicted, okay? Because you want, in the AP exam on the free response, when you're interpreting these things, since these are predictions, you want to include the word predicted, okay? So the predicted price of the Ford F-150 goes down because it's negative, right? So it's a negative sign there, so it's going down here. And it goes down by 0.1629, which is 16.29 cents if you think about it, for each additional mile driven. Again, you can put that number over an invisible 1. And remember that the top is y, and here y is the price. So this is in dollars, and the x is in miles, okay? So it's going to be for every mile, additional mile. All right, now we're going to interpret the y-intercept. The y-intercept is that first number, 38,257. And remember, that's when the miles driven is 0. So when the predicted price of a Ford F-150 that has been driven 0 miles, I really should have put it here. The predicted price of a used Ford F-150 that has been driven 0 miles is $38,257. Okay, so I forgot to include that there. So the predicted price is $38,257 when it has been driven 0 miles. Here, the y-intercept does have meaning because it is possible to have something that's not driven at all, right? Zero miles driven means it's not been driven at all, means it's brand new. So if you have a brand new Ford F-150 and you take that out of the lot, that's it's a $38,000 tag, right? Essentially, and then it's going to decrease in price when you continue driving it. Caution, a cautionary note here: when asked to interpret the slope of the y-intercept, it's very important to include the word predicted, like I mentioned here. And then otherwise, it might appear that you believe the regression equation provides actual values when it's not actual values, it's predicted values. And of course, you want to include context here, right? All right, so now let's take a look at, go from regression line to the least squares regression line. So now we're looking at least squares. So what is that? Well, we know that there's different lines that we can use, different models, right? Different regression lines, if you will. But which regression line is the best? The best one is the one that is known as the least squares regression line. So let's take a look at the data for the Ford F-150s here. And you can see that there's a bunch of residuals here. So each of these bars that you see that go up and down are my residuals. So they're my errors, okay? And what you see here with the squares are, these are the squared residuals, okay? So basically, if the residual here, for example, that one we said was, this value was about 35,000, right? And this value here, we said was about 27,000. We mentioned earlier that the residual here is $8,000, right? And so what we're doing is we're taking that residual and we're squaring it. And so we construct geometrically, that means we construct a square that is 8,000 by 8,000. And the area of that square is 8,000 squared, okay? That's what those squares represent. So those squares represent squared residuals. So that's why we have this here, squared residuals. And so what we want to do is we want to add up all of the areas of these squares. So we want to add up each of these areas, right? So the area here plus the area here plus the area here and so on and so forth. And that gives us my sum. So my sum of squared residuals, okay? Sometimes we shorten that as SSR, okay? Sum of squared residuals. And so what we want to do is we want to minimize the sum of squared residuals. We want to make that number as small as possible. If we take another line and we do another regression line and we find the sum of squared residuals to be greater than, so for example, if I have this red line and I find that the SSR is greater than, then that means I want to reject that line, okay? So I want to take the line with the smallest squared residuals, okay? So a good regression line makes the errors as small as possible. The regression line we prefer is the one that minimizes the SSR, the sum of the squared residuals. And that is referred to as the least squares regression line, okay? So it's the line that makes the sum of the SSRs as small as possible. All right, so, and we're going to talk about how to calculate that regression line in a second, but right now we want to focus on just the definition and what the concept. So here we want to talk about a residual plot. So if I have a linear model and I want to determine if whether it's appropriate, I can use something called a residual plot. A residual, remember, is an error, right? So a residual plot plots all of the errors onto one graph. So basically we take all of these residuals, right? All of these differences from the data points to the graph, and we graph those, okay? So for example, this one we said was roughly 8,000, right? That's the one that we've been using. Well, that was for a distance of around that's 60, about 70,000 or so. So that would refer to, if you look at the data point, that would refer to this data point right here, which is roughly 7,000. Okay. So that point right there is represents the residual of 8,000. Okay. So basically you take all the residuals and you plot it. Now some residuals are positive and some are negative. So we have 0 in the middle and we have some negatives and positives, right, above and below. And what we want to look for in a residual plot to determine appropriateness is we want to see randomness. So I want to observe that the points are random, meaning that there's an equal chance that they will be above the 0 line as well as below the 0 line. If I see randomness in the graph, that tells me that the linear model is appropriate. We want to see that the errors are random. We never want to see errors have a pattern, because if errors have a pattern, that means that we have a pattern in making incorrect estimates, right? And that means that our model is most likely not going to be appropriate. Okay. So we want our errors to occur by chance alone and not by a systematic method that we're doing, okay? If that makes any sense. So we want it to be random. So essentially we want to see 50% of the points above, 50% of the points below. That gives you an idea of randomness. So we don't want to observe any patterns. So a residual plot magnifies the deviations of the points, making it easier to see unusual observations. So for example, let's say we have this scatter plot, which you can see that the best model for that would be a curve, correct? You can see that it clearly is inappropriate to use a linear model for this, you can see. We can also observe that in the residuals. So here we have a clear pattern of over prediction. Remember, if it's underneath the 0 line, it's an over prediction. So this is an over prediction. And if it's above the 0 line, it's an under prediction. And so we can see a clear pattern of over prediction, under prediction, and then going back again to over prediction. And it's very systematic, right? It's very pattern based. If you see patterns in the residuals, that indicates that the regression line or the linear model that you're trying to test is inappropriate. So the residual plot should show no obvious patterns, and the residuals should also be pretty small. They shouldn't be large. So here, this is the patterns in residuals. We can see that there's a pattern, and therefore the linear model is not appropriate. All right, so how do we interpret a residual plot? Let's summarize. To determine whether it's appropriate, look at the residual plot. If there's no leftover pattern or curved pattern in the residual plot, then it's probably going to be appropriate because there's no pattern in the residuals. We also want to look to see if there is a leftover curved pattern, then we want to consider using something else. So we don't want to use a line, maybe we want to use a curve, right? So these are things you want to keep in mind. All right, so here we go. Let's look at an example of using the Ford F-150 data. This is the residual plot for the set of data that we looked at earlier. So here it is, the residual plot. Now, is the linear model appropriate? Well, if you look at it, let's see how many dots are above, how many dots are below, and look to see that there's clearly a pattern or a lack of pattern. So here we got 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got 9 dots here. Here, 1, 2, 3, 4, 5, 6, 7. All right, so 7. So that's a pretty even ratio. I mean, it's not going to be exactly 8 and 8, right? Because it's by chance. So 9 and 7 looks pretty random, okay? And again, it's going to be obvious if there's a pattern or lack thereof, right? Most of the time. But you can see here that there's roughly half above, roughly half below, and it's not like it's alternating or anything. I mean, it's just random. And so there's a lack of a pattern. So there's no obvious pattern left over in the residual plot, so the linear model is appropriate here. Okay. How well does the line fit the data? So now what we want to see is, well, okay, so we determined that it's appropriate to use a line with the residual plot. well, then how well does the line actually fit the data, and how well does it, how well does the data, each of the data points fit to the line, right? And so what we want to do is we want to consider all the residuals, not just one, right? And so what we want to do is, like, looking at all of the residuals as a whole, we can see what is the typical prediction error that we make. Is that typical error high, or is that typical error low, right? So on average, is my prediction high or low, my error? And so what we want to do is calculate the standard deviation of the residuals, okay? So again, the standard deviation of the residuals measures the size of the typical error or residual. How big is my typical error? Is it on average 5, or is it on average as high as 15, right? If I have a standard deviation residuals that's very high, that means the line is not doing very well, right? It's making a lot of errors. So S measures the typical distance between the actual y and the predicted y's. So remember that y minus y hat is my residual, right? And so what we want to do is we want to find the sum of the squared residuals, right? So, and then we want to divide by n minus 2. This is important because in the traditional standard deviation for x or y, the standard deviation was the sum of the x values minus the x bar values divided by n minus 1. Okay, so that was the formula for the traditional standard deviation for unit 1, right? And we used n minus 1 on the bottom. Now here we use n minus 2. And the reason being is that we're dealing with two variables, x and y. And so you want to account for those two variables by subtracting 2 instead of 1 here, okay? So that's something to keep in mind. All right, so here when you're doing standard deviation residuals, just remember to divide by n minus 2 instead because of the two variables that we're dealing with. All right, so now the standard deviation of residuals gives us an estimate of the average size of our prediction errors. So that's how you would interpret it. Okay, so another quantity that helps us to see whether our least squares regression line makes good predictions or how well it does predictions is something called the coefficient of determination. The symbol for that is r squared. So the coefficient of determination r squared, what it does, there's two interpretations for it. The first interpretation is it measures the percent reduction in the SSR, the sum of squared residuals, when we use the regression, the least squares regression line to make predictions, rather than the mean value of y. I'm going to explain what that means in just a second. We're going to look at a graph to visualize this. The second interpretation is it measures the percent of the variability in the response variable accounted for by the least squares regression line. Those are my two interpretations. We're going to show you what the first one means for the interpretation. Okay. So here's how we can interpret that, that first explanation. So this is the original data for the Ford F-150, right, on the right. And we got the least squares regression line here, and you can see that we're doing our sum of squared residuals, right? So these squares are my sum of squared residuals for y hat. So that means that the residual are the errors, right? So how far are these data points from the actual prediction line here, right? So the sum of squared residuals for that was 461,264,136, okay? That seems pretty high, but remember that this is the least squares regression line, so this is the lowest that we can get to that. We can't get any lower than this. Any other line would have a greater sum of squares. Now, if we instead of using this least squares regression line, if we instead use the average, this is the average y bar. So this is y bar and this is y hat, okay? Which is the a plus the bx, right? If we instead use the average value rather than the y hat, here the average value of the Ford F-150s was approximately $28,000. Right? So that was what the average is. This line right here represents the average. So if we instead find the residuals from the average and use our average as our estimate, then we can see that we're making a lot of errors here, right? So these data points, all of these have some kind of error, right? From the average there. This one doesn't have that much of an error. These points don't have much of an error, but then these points do, right? You can see that. So if we use y bar as our prediction line, quote unquote, then our SSR skyrockets. You can see that it skyrockets to 1. In this case, before it was 461 million, now it's 1,373,000,000 and so on, right? So it's way bigger. So what happens is when we switch from y bar to y hat, what percent does our error get reduced? So when we switch from this sum squared residual to this, what was the percent reduction in the error? That's what the R squared tells you. Okay, so the R squared tells you that reduced error. Okay, so in this case, the percent reduced error would be as follows. We would take R squared, to calculate the R squared, we would take the so we would take the 1 billion number minus the 461 million number, and that tells us how much it got reduced, and then we divide that by the 1 billion number, and then that tells us the percent that it got reduced. Okay, from the original 1 billion, how much did it get reduced, right? What percent reduction? Okay, so this is going to be a decimal, which we can convert to a percent by multiplying by 100. So that's what the R squared tells you. So here's the formula. The other way that we can say is by using the SSR, right? So SSR means sum of squared residuals, right? So this is the SSR for y bar right here. So this here, let me get rid of all these. There's so many arrows here. So this is the SSR for y bar, right? Because this is where we use y bar. And this is the sum of the squared residuals for y hat, right? Because this is where we use y hat, the equation. And so we could subtract those. So that's what this formula is saying. So this formula is exactly what we just did over here. All right, and so that's what R squared tells us. That's the coefficient of determination. So remember, SSR stands for sum of squared residuals. Okay, so hopefully that made sense with the graph. So let's look at the Ford F-150 and look at the, here they tell us that the R squared is 0.66. Again, we could have calculated that by doing what we did over here, right? We can calculate that to see if that's the actual one. I'm not sure if this is the actual data, the actual numbers for the F-150, but I do know that this was taken from the book, and these were the numbers that were provided. But here they said, okay, well, the technology gives us these values. And by the way, we're going to, later on in this video, we're going to show you how to calculate R squared in more detail if we're given data. All right, but for now, let's just say they give us those values. Interpret what S means, interpret what R squared means. Okay, so S is the standard deviation of residuals. So let's interpret it. So remember, S is the typical error that we make, right? The average or the typical residual. So we're going to say that the actual price of the Ford F-150 is typically means on average about $5,740 away from the price predicted by the least squares regression line. Okay, so remember that the equation for S, right, was square root of the sum of the residual squared, which was y minus y hat, or y hat here, squared. This should be a y hat, sorry about that, divide by n minus 2. So this tells us the typical distance from the predicted line, right? So the actual price is typically about 5,740 away from the predicted y hat, right, by the least squares regression line. Okay, so that's the interpretation of S. Now R squared, the interpretation of R squared is what we talked about earlier, is the percent reduction when we get from the average price of the Ford F-150 to the least squares regression line. Okay, so the first interpretation is, so the first interpretation is that there's a 66% reduction in going from the y bar to the y hat. The second interpretation, if you recall, is talking about the variability. So about 66% of the variability in the F-150, Ford F-150, is accounted for by the least squares regression line. Okay, so again, the other way that you could, this is the second way that you could interpret it. The first way that you could interpret it is that there is a 66% reduction in price of the Ford F-150. I'm not going to write all that down. When switching from the average price to the least squares regression line. Okay, it's not so it's something like that. It's how it goes, right? So if I go back to the first interpretation, you go back to the first interpretation, it kind of looks like this. All right, so those are the two various different interpretations of R squared, but they mean the same thing. So now what we're going to look at is what happens if we have a problem where they give us computer outputs. So sometimes you'll see a free response question or maybe a multiple choice or something like that, and they'll, but usually a free response, and they'll give you a computer output like this, right? Here they're saying constant. When you see constant and then you see here the miles driven is the variable. So miles driven is variable. So that means that that's my X, right? Constant means that it's a constant. So remember that the equation of the regression line is y hat equals a plus bx. So in terms of the computer, this is my constant and this is my slope. So this is my variable. So the miles driven, this is actually telling me my slope. The constant is actually telling me my A, right? So it's giving me my y-intercept. So that's how you read the computer output. Obviously, R squared is the R squared, the coefficient of determination, and this S is the standard deviation residual. So it kind of tells you in there. All right, so here's another output, another way that they could say it. Remember that the standard deviation formula for residuals is the square root of the sum of the residuals squared, right, divided by n minus 2. So in other words, it is also known as a root, because you're taking the square root, a root mean square. It's called a mean because you add the residuals together, divide by how many you have, except it's n minus 2 instead of n. So it's root mean and square because it's just, you're squaring it. All right, so when you see that in the output here, root mean square, that is referring to your standard deviation. Here in this case, standard deviation of residuals. All right, obviously R squared is your R squared value. And then you have your intercept, that's your A, miles driven, that's going to be your B. All right, so just know how to interpret the various computer outputs. All right, so here we go. How to calculate the least squares regression line. So let's go ahead and calculate it. We know that the equation is y hat equals a plus bx. How do we calculate a and b? So first off, we need to calculate b. B is the slope. To calculate b, we take the correlation r, the coefficient r, and we multiply by the standard deviation of y divided by a standard deviation of x, okay? They'll give you those values, and then you can, maybe they'll give it to you in computer output or whatever the case may be, and you can just plug it into this formula to get the b. We can also show you how to calculate sy and sx by hand, which we'll show you in later on in the video. But you can, you know, in some examples, they'll actually give those to you, and then you can just plug them in to get b. All right, so here we go. Now, once we get b, we can take whatever we get for b and plug it into the equation for a. All right, so to get a, we take the average for y minus the b that we got earlier times the average for x. All right, and those are the two formulas. Once you calculate those, then you can just plug those in. You got your a, and then you got your b, so it's going to be a plus bx. All right, so let's look at examples. So Hazel travels through several intersections with stoplights on her daily drive to work. For 20 days, she records the number of green lights she encounters and her total commute time in minutes. The correlation between the number of green lights and the total commute time is negative 0.491. So I guess that would be, you know, in the moderate to moderate weak side. You know, once you get to 0.5, we usually call that around moderate. For these 20 days, her mean total commute time was 59.5 minutes with a standard deviation of 12.5 minutes. And the mean number of green lights was 11.1 with a standard deviation of 4.7. All right, so they're giving us a lot of things here. They want us to find the equation of the least squares regression line, interpret the slope and y-intercept. All right, so first off, what is the explanatory variable? The explanatory variable is the number of green lights. The number of green lights will help explain the total commute time. So if there are not that many green lights, we would expect that the total commute time would increase because she's hitting reds. If the number of green lights increases, then her total driving commute time decreases. All right, so x is the explanatory variable for the number of green lights here. All right, so in that case, the x bar that they gave us is 11.1 because that's the mean for the green lights, which was the explanatory variable. And then this has to be my sx, right? My 4.7, and my sy has to be the other one, the 12.5. All right, and then the n equals 20. That was 20 days that she recorded her data. And so that's how we get each of these from the word problem here. So now we can calculate my slope by plugging in those numbers. We got our coefficient, we got our sy on top divided by sx. We get about negative 1.3 for my slope. Now for my a, we can take the number here, and notice I didn't plug in negative 1.3 into here. Instead, I plugged in the negative 1.306. You generally want to plug in as many decimals as possible as when you're trying to calculate a different quantity, right? If you can put negative 1.3, but it will affect your a slightly. And so in order to get a more accurate or precise a value, make sure that you include as many decimals from your b calculation into your a calculation. All right, so here we got our y bar. Our y bar, in this case, our y bar is 59.5. My b was this number earlier, and my x bar was 11.1. And we get an a is about 74.0. So we can plug these into my equation, right? Y hat equals a plus bx. All right, because we know a and b, and that's our least squares regression line right there. And so now what we're going to do is we're going to take that and we're going to interpret the slope, right? So let's rewrite the equation. So it was y hat equals let's go back. It was 74.0 minus 1.3x. So the slope is clearly negative 1.3. So it's negative 1.3 over an invisible 1. And remember, its slope is rise over run, so rise is y. So the y is the number of minutes, and the x is the number of lights, so the green lights, right? So for every increase in one green light, we get a decrease of 1.3 minutes of total commute time. You also want to use the word predicted, okay? Because these are predictions, all right? They're not exact. So the predicted total commute time decreases by 1.3 minutes for every increase of one green light. The y-intercept is 74. And so when x is 0, we would expect that the predicted time would be 74 minutes. This makes sense because it's possible to have no green lights at all. It means she's hitting nothing but red lights, and so that's going to increase her commute time to a maximum of prediction around 74 minutes, which is pretty high. All right, so that's our interpretations. So now let's look at a couple of notes here. So correlation and regression lines, there's limitations to them. Correlation and regression lines describe linear relationships. Correlation R, the correlation coefficient R, is only for lines. You cannot use this for other curves, for curves and things like that. You have to only use it for lines. So when we look at the correlation coefficient, it actually doesn't tell us, it just only tells us the relationship for lines, okay? So like if you look at this example, technically all of these data, collections of data have the same equation for the least squares regression line. if we fit it to a line, right? So technically, these all have the same equation for a line. And I mean, and again, this is just an estimate that I'm doing. So they all have the same type of line, right? Same equation, same R value, right? Because the R value is only telling you the linear relationship. So if there were a line, how close would it fit to the data, okay? So it is possible to get the same R and the same equations, even though you don't have any even though you have curved data versus data that looks linear. So you just want to be careful and be mindful of that, you know, this limitation. All right, so correlation and least squares regression lines are not resistant. So that's another limitation. Another thing to keep in mind is that if I introduce an outlier, that will affect my correlation. That will also affect my least squares regression line. And so we want to look at some special points. So there are points that have high leverage. Points with high leverage have a great effect on the graph, on the regression line. What these points are points that have really large or really small x values compared to the rest of the data set. So those are called high leverage points. They're so far out from the data, they actually have high leverage because they guide the line in a certain sense. We'll look at that an example of that later. An outlier is another influential point, and it's when you have something that strays from the overall pattern. So generally it has a large error, large residual, and it strays from the pattern immensely. So an influential point are both of these. So technically both of these are influential points because they affect one or more things, right? They affect either the slope, the y-intercept, the correlation, the r-squared value, or the s value. Okay, so it could be either one of those, any combination thereof. So those are known as influential points. All right. So note, if two things are associated, that does not imply that one caused the other. So for example, the Ford F-150 example or whatever, we can tell that the number of miles driven generally does decrease the price, right? But imagine that there might be other factors involved, right? So it might not be a direct cause and effect. In that case, it may be a direct cause and effect, you know, for the Ford F-150 example. But consider other examples where you see a strong association, but one variable didn't necessarily cause the other variable. Okay, so you never want to assume that one variable causes the other just because there's a strong association. All right. One example of this is the shark attacks ice cream example, right? As the ice cream sales increased, the number of shark attacks increased, but that doesn't necessarily mean that they caused each other, right? It could have been some other variable. All right, so a strong association between two variables is not enough to draw conclusions about cause and effect. This is what we were saying. Just because you have a strong R value doesn't mean that you can draw cause and effect, all right? Okay, so let's look at a few cases here for outliers and influential points. So the first case is when you have no outliers, you just have your data set, okay? So let's assume that we don't have any outliers, we don't have anything unusual, we don't have any influential points. Then in this case, the R squared, the R value is 0.41 for this data set. It's not terribly strong, right? It's like on the moderate side, you know, going onto the weaker side, right? So, but here's your equation, right? Here's your equation of your least squares regression line, and there's your R value. So nothing influential here, right? Now, what happens if I introduce an outlier? So we're going to look at case 2, right? So if I introduce an outlier, or let's look at the case 2. So what happens for case 2? So for case 2, here we go. So basically we're, and this is an animation, and it's going from case 1 to case 2. So we got case 1, and then we introduce case 2 there, right? But notice what happens when we go from the original to case 2. What happens to the equation? Well, the equation stays the exact same. And the reason being is that this point is actually very close to that line, right? So you'll see that drawn. So it's not going to really affect the graph at all. This is an influential point Because that point is actually strays very far from the data, right? It's very far from the data, and it has a large x value. Okay, so large x. So that's technically an influential point. So it's a point that's far from the others in the x direction, but it's in the same pattern as the data. So notice that there's very little to no change in the graph. However, because it's an influential point, it actually immensely increases the r, because now we have a point that's so close to the line, it's making the r values really high, which is a really good thing, right? So this point is actually helping us get a better model. And then it increases the r squared immensely as well. Now notice, look at the standard deviation of residuals. It decreased in case 2, and that's because now that we have this influential point that is so close to the graph, it's going to decrease the residual overall, right? So overall, the residual is being decreased slightly because this point is very, very close to the line. So it decreases the average error, if you will. Okay, so this makes sense. So this is case 2. So let's look at another case, case 3, and looking at this animation, right? So from the original case 1 to case 3, where we introduce an outlier somewhere down here, right? Notice what happens to the graph. The graph goes from positive slope to negative slope. So here we go from a positive r to a negative r. And that changes the regression line immensely, as you can imagine. Look at the big change in the slopes here, negative 0.09 and 0.65, right? So the graph changed, the equation changed immensely. Also, take a look at the r squared value. The r squared value did not change very much. It turns out that when I introduced this point here, it's still the same average. If you look at the r's, the r value didn't change that much. It changed from positive to negative, of course, but it didn't change overall as far as 0.3 versus 0.4. It's not much of a difference when we're talking about line of best fit, right? So it didn't change very much, except for the fact of the sign change. And so we expect that the r squared does not change very much as well. All right. However, the standard deviation increases slightly here because now what the new line does is that this line is now farther away from those than it was before. You see that? You can see the difference there. So let me look at this point from here to here compared to where it was there. You see, it's closer in the original case than it is in the new case. And so that accounts for the slight increase in the standard deviation. Okay. All right. Also, something to note is that if you have an outlier, or in this case, this is an outlier, right? This point is an outlier because it strays very far from the original pattern, right? The original pattern, you can see that. Now, if you see a value that's well below or above the line, that is going to tend to make the line go in that direction. Okay, so now you can see that the line is going downward in the direction of the outlier, but it's swiveling. So this part is decreasing while this part is increasing slightly. So you can see that slight increase on the left end and a decrease on the right end. And so what that does is that it increases the y-intercept. So if you look at the y-intercept here, the y-intercept slightly increased, whereas the slope got decreased, right? The slope got flatter. So this line is less steep. Okay, so any outlier that goes above or below the line and that is far away from the data values in the x direction is going to swivel the line, is going to pivot the line rather. So it's going to pivot it. All right. Also, so going back to the other example, so if I go back to case 2, this one was on the line, so it didn't really pivot it, right? Because it's pretty close to being on the line. All right, so now let's look at case 4, the final case. Here, we got an outlier introduced above on top here. But notice that most of the data is here, right? Most of the x values are there. So this is very close to the data in the x, right? In the x direction. However, in the y direction, it's very far away from the data. And so what that does is that it tends to pull this line up. So we're going to take this line and it's going to pull it up. And you can see that has that pulling up direction. So if you have a point that is above the line and it's very close to the data in the x direction, it's going to simply pull the line up. Now, if you have an outlier down on the bottom, let's say down here, for example, and it's very close to the data in terms of the x value, well, then that's going to pull the line down. So it's going to have the opposite effect, okay? So that's just something to keep in mind. So if it's very close to the x, but it's above or below the line, it's going to pull the line. If it's very far away from the data in the x direction, and it's below the line or above the line, it's going to pivot the line. So the line is going to swing. It's going to have a swinging action. So if you can see here, the slopes are the same, but instead this is increased because the line is getting pulled up, right? All right, so that's the difference in the equation. Now also notice that when we have that outlier, or we have that, that's an outlier, the r decreased immensely because now we have a point that's so far away from the line. That's going to decrease my correlation, right? My correlation is very bad now. So that decreased immensely, and so did the r squared as a result. So this decreased immensely. Also, this increased immensely because if you look at it, because of the error. So now we have a large error from here to there, and therefore that's going to increase my s, right, if I take into account the outlier. So hopefully this makes sense. This is a detailed discussion of each of the how influential points influence each of these characteristics, right, of the regression line. All right, so let's look at an example where we apply what we just talked about. So using the data given, determine which of the 2 points, child's 18 and 19, have high leverage or is an outlier. So in this case, if you look at child 18, it is very far away from the data set in the x direction, and so it's considered an influential point, right? It's very far away in the x direction. It's considered not an influential point, a high leverage point, right? A point with high leverage. And therefore it is an influential point, but more specifically, it's a high leverage influential point, right? So that's a high leverage. That's a point with high leverage. Now with child 19, it's very close to the data in the x direction, but it's above the line. It's far above the data in the y direction, right? It's significantly above the data in the y direction. And so this is an outlier, right? Not a point with high leverage, but it's an outlier because it strays from the data. So the point for child 18 has high leverage because its x values is much larger. The point for child 19 is an outlier. It falls outside of the pattern of the other points. These are both influential points, but they're different names. And you can see that the child 19 has a very high residual, and so therefore it's expected to be an outlier. Child 18 does not have a high residual. However, it does have a definite increase in the x compared to the rest of them. It's far away from the data. All right, so now using the data given, describe the effects. So what happens if we remove child 18 and then remove child 19 separately in separate cases, okay? So let's go ahead and remove child 18. Now remember, child 18 is far away from the data in the x direction, but it's below the line. And so since it's below the line and it's far away from the data, it's going to have a swinging effect. So it's going to swing this line. The line is going to swing down towards, on the right end, it's going to swing down towards the child if that data wasn't there. So if I ignore that, right, and then I introduce the outlier now, right there, then this line is going to swing here and it's going to swing there, right? However, the outlier is already there. So if I remove the outlier, it's going to have the opposite effect. It's going to make this swing up there, and it's going to make this swing down, okay? So because here we're removing the outlier, it's going to have the opposite effect of what we would suggest. Okay, so the line may end up looking something like this, right, where it swings. Okay, so child 18 is going to have that effect. All right, so removing point for the child 18. If we remove it, that means this is going to go up, this is going to go down, which means that the y-intercept decreases. That also means that the slope gets flatter, right? So it becomes less steep. So these are things that we want to keep in mind. So it makes the slope closer to 0, flatter. It makes the y-intercept smaller, right? Decreases. It slightly increases the standard deviation. Why does it do that? Well, because if I remove the outlier, right, if that's not there, well, then this line is going to have, you know, it's going to have a different, you know, like distance from each of these points, right? And so, for example, here we had some small distances, some small residuals here, but when the line goes flat, now these residuals increase, right? And so we end up having some increased residuals. Even though some of them decreased, there's ones that are that increase a little bit more. Now it's slightly increased, so it's actually not very large, okay? So it might be only like 0.1, 0.2, but it's still there nonetheless. All right, and then greatly decreases the r squared. The reason why it greatly decreases it is because now, because of this new line, we have a decreased correlation. Because remember, this child 18 was an influential point, which means it actually increased the r, right? Because it made the data fit closer. But if we remove it, now we don't have that influential point anymore. I said outlier, I meant to say influential point. Now we no longer have that influential point, and so that's going to decrease my r overall, which means it is going to decrease my r squared, okay? Hopefully that made sense. So now we're looking at child 19, which is close to the data set, right? It's close to the data set in the x direction. However, it's significantly above, right? And so what that's going to do, it's going to pull the line up. And so the slope of the line is going to be about the same. It's just going to be pulled up like this. Okay, so it's just pulled up a little bit slightly. So that means that the y-intercept increased, right? If child 19 were below, then it would decrease the line. However, remember, this is if child 19 was not there. If child 19 was not there and I introduce it, then it's going to pull the line up. If it's there and I remove it, it's going to have the opposite effect, right? And so instead of doing the increase, if I remove it, it's going to have the opposite effect. And so it's going to make the line go down. And so now our final answer is that it decreases the y-intercept. Okay, so hopefully that made sense. If the outlier wasn't there and I introduced it, it's going to make it go up. If the outlier was already there and I remove it, it's going to make the line go down. The opposite. All right, so it barely decreases the slope. It doesn't really change it very much, right? It's mostly the same. It barely changes. Here it changes the y-intercept. It decreases it. So I'm going to put decreases there. Decreases the y-intercept if we remove it. Although it's not going to be that much of an effect because, you know, it's significantly above. It's decently above, but it's not that extreme above, right? So if child 19 were here, then it would have a much greater effect if it's like over up here in the 140s, right? But it's still going to decrease it's still going to change the y-intercept. It's going to decrease it. I need to put here decreases the y-intercept. All right. And then it greatly decreases the standard deviation of residuals. Why does it do that? Well, because the reason it decreases it is because if I remove that outlier, that means that's no longer there. And so now look how small the residuals are. The residuals now become much smaller now that we don't have that outlier. And therefore, this is going to greatly so it'll greatly decrease the error, right? So remember, decreasing the standard deviation is actually a good thing because that means the data is better overall. It's closer to the the line. So if I remove that outlier, obviously the data is going to be closer to the line on average. So it's going to decrease it. And also because the data is closer to it on average, it's going to increase my R, right? And so that's going to increase my R squared. All right. So if we remove outliers, that tends to increase R squared. It tends to decrease standard deviation. And it tends to have some impact, depending on how big the outlier was to begin with, to the y-intercept, slope, things like that, right? But it just kind of really depends on how big the outlier is. If you're removing an influential point, that's going to, in general, tend to decrease R and R squared. It may have an effect. It may have a small effect on the standard deviation, but it'll definitely change the slope, right, if you remove that, and therefore the y-intercept. So those are things to keep in mind. Okay, so we are officially done with the lesson. Now what we're going to do is a couple of extra examples of how to actually calculate using the calculator, the TI-84 at the end, but we're also going to show you how to actually calculate these by hand. So here's an example of battery life of a tablet, of tablets. So we have a sample of 15 tablets. We have the least squares regression line. Let's say we have that line already. We're going to construct a residual plot. So first off, I'm going to show you how to find the least squares regression line on the calculator later. I'm also going to show you how to do residuals. I'm going to show you how to calculate the coefficient of determination. So I'm going to show you how to do that just given the data, x, y. So like it's very detailed in calculations, okay? So, all right, let's do the residual plot. So residual plot measures residuals, right? So residual means I got to do y minus y hat. So first off, I need to find my y hats, okay? How do I find my y hats? Well, I take the x value and I plug it into here, right? And that gives me my predicted y hat. And so if I plug that into that equation, I get 7.64 hours of battery life. And you can see that equation over here. The next one is going to be 500. I got to plug 500 into there. And if I do all of those, I get, so if I put 500 into there, I get 8.03. If I plug in 475 into there, I get 7.83. All right, so this is how I get my predicted battery life. Now I need to do my y minus y hat. So I got to subtract those two. All right, so I'm going to do this y minus y hat gives me my residual. Okay. So if I subtract that, I get 1.10, and I repeat that for this. So if I subtract these two numbers, I get that number, all right, and so on and so forth. All right, so now I got my residuals. These are my residuals, right? And so now I'm going to graph the residuals on the residual plot. So this is my residual that I calculated earlier, and these are my x values, my price of my tablets. So generally, we would expect that the greater the price, the better the battery life, right? Or maybe, right? So let's see if that's the case. So if you look at the data here, generally as this increased, the battery life tend to increase, right? So we can see that. So let's go ahead and graph the residuals. So keep in mind that price was on the x-axis because that's my explanatory variable, and residuals are going to be on my y-axis. So we got a positive 1.10 for a price of 450. So right here around 450, we got a price of 1.10. So we should have a dot right around there. For the second one, we have a price of 500 and then a residual of around 0.54. So it's going to be right around there. And you're going to keep repeating this until you get all the residuals. So here you go. These are the residuals. These are all the points plotted. And so now you get an idea of the residual plot. And so is this, if I look at this, is a linear model appropriate for this? Well, if you look at this, we got 1, 2, 3, 4. We got 4 dots here. 1, 2, 3, 4, 5, 6. We got 6. So this is roughly a 50-50 split, guys, which means that a linear model is probably going to be appropriate. And there doesn't seem to be a pattern in the errors, right? They seem to be random, and therefore we would expect that the linear model is appropriate. Okay, so because the residual plot appears to be random, no visible patterns, the least squares regression line is an appropriate model for the data. Right, So that's important. So now I showed you how to actually do the residual plot by hand. By doing, you can of course use the calculator to, do the stuff in between, but at least you know how to set it up. All right, now we're going to show you how to calculate the standard deviation of residuals. Remember, the formula for that is the square root of the sum of the residuals squared divided by n minus 2. So we got to find the y hat, which we've already done in the previous lesson, or in the previous slide. We got to find the residuals, right? We already know what the residuals are. We found this earlier when we did the residual plot. So we actually already know what these are. And then I got to square them. So I got to square them and then add them, right? Then divide by n minus 2 and then do the square root, obviously. Okay, so we've already done this in the previous slide. So I'm just copying and pasting the data. Now I'm going to square these numbers. So I'm going to introduce a column to square it. So this is that same thing, but squared. So I take this and raise it to the second power to get that. Here's your work for that. And you rinse and repeat. So you're going to take this number, square it to get that, right? Take this number, square it to get that. Now we're going to get the total of this column, right? So that's going to be my sum, right? We're going to sum this column to get 13.01. Then we're going to take that and plug it into our numerator, keeping in mind that the formula is the square root of the sum of the residuals squared divided by n minus 2. And so the sum of the residuals squared, that's 13.01, so that goes in the numerator, right? Divide that by 10 numbers. I got 10 numbers here. Or actually, it should be 15 tablets, right? So let me change that number. Oh, okay, so this should say 10 tablets, not 15 tablets. So the error is in the question itself, so I apologize for that. So we've done using data from a sample of 10 tablets. Okay, so we got 10 tablets here. All right, so it's 10 minus 2, and then it's going to be 1.28. So 10 tablets for this guy. All right, so my standard deviation is 1.28. That's kind of low. I mean, it just kind of depends on the data. So like the battery life are in the order of tens of hours, right? Maybe 8 to 10 hours or so. So maybe 1.28 hours is significant depending on the type of data you're looking at. All right, but there's my average spread in the battery life, the predicted. All right, so now we're going to calculate the coefficient of determination. So now, first off, we need to know this. So we're going to keep that from the previous slide. Remember, the coefficient of determination, the formula for that is the sum of the squared residuals using y bar minus the sum of the squared residuals when we use y hat, divided by the sum of the squared residuals when we use y bar. Okay, so we already know what this is because we calculated that. We are trying to find this now. So first off, we got to find what y bar is, and then we got to do y minus y bar, then we got to square it. Okay, so let's figure out what the y bar is. That's the average of this data, the battery life. So you add the battery lives together, divide by 10, and you get 8.88 hours of battery life. Next, you're going to take the y value and you're going to minus it by the y bar. Okay, that's what we're going to do. So we're going to take this minus this. You can see that in the formula there. And we get negative 0.15 hours. And then we repeat that for the rest. So for this, now we're going to do this minus this gives us that, right? And so on and so forth. All right, now we're going to take these numbers and we're going to square them. All right, that's what we're going to do next. All right, so we take this number and we square it to get that. All right, same thing there. We're going to square this number to get that. All right, and that's what you get when you square them on the calculator. Now we're going to find the total for this column, and we're going to find the total for this column. Now we already found the total for this column earlier, so we're going to reuse that number, but we haven't done the total for this one yet. Okay. All right, so the total for this one we said was 12.69. Actually, I don't think we did the total for this, but we're going to do it now. So we're going to add those up. Maybe we did the totals. I can't remember. Let's go back. So we did that when we did the 12.69. Oh, so this should say 12.69, not 13.01. So just want to verify that. This should say 12.69. Yeah, so this should say about 12.69 instead of 13.01. So it should be approximately 12.69 divided by 8. So if I end up calculating that, I get approximately 1.26, which is not that far off from what I got there. But I did want to correct that, so I apologize for that. So if I go back here, we have 12.69 for the total here. 12.69, 12.7, it's around there. And then the total for the last column is 24.65. Look at that increase when we get from there to there. That's telling you that there's going to be a big decrease in the percentage, right? And so that means that's going to obviously increase the R squared. All right, so now we're going to take, we know those two values are 24.65 and 12.69. So we're going to plug into my R squared formula, right? So we got 24.65 minus 12.69 divided by 24.65. And we get an R squared value of about 0.49.5. Okay, so it's a roughly 49% decrease. So the sum of squared residuals decreased by 49% when we switch from the mean battery life to the regression line. So when we switch from y bar to y hat, right? So that's the what the R squared is. The second interpretation is that 49% of the variability in the battery life is accounted for by the regression line. Those are my two interpretations. Hopefully that made sense with the calculation for coefficient of determination. Now we're going to show you how to do this on a calculator. And then we're going to end it here. Again, this is for 10 tablets, not for 15, so we just make that correction. But now we're going to verify this. How do we know that that's the equation, right? How can we calculate that if I give you x and y data? Well, all right, so in order to do that, we can use the TI-84. We can use the calculator to do this. So let's show you how to do that. So first, we are going to use the statistics. We're going to edit. We're going to type in all our numbers into there from the price and the battery life. Once we do that, we're going to exit out, second mode. Then we're going to hit stat. We're going to go to calculate. We want to go to number 4, linear regression. We want to choose list 1, list 2. We don't have to change anything. Go to calculate. Then that is my equation, right? You can see that. 0.0079 and 4.08. Next, you want to go to vars and statistics. Then you want to go to equation and then go down to R squared. And enter, and that will give you the R squared value. So you can pause or rewind if you need to see that. But that is how you get your R squared value. And that's pretty much what we got. We got about 0.48, 0.49-ish, right, for my R squared. All right. So I hope you found this lesson informative and useful. There's a lot of information packed in there. But as usual, I'll see you in the next one.